Okay, hello everyone. My name is Hong, and here we have my co-presenter Kaishi with me. We are both product engineers from Esri development. We work on processing time series imagery and multidimensional Raster project. In this presentation, we're going to cover the capabilities and APIs that we have developed in ArcGIS Pro 2.5, which has been just released early this year. So this presentation is a very new topic. ArcGIS is a platform for imagery. So first, we'll go over the image capabilities that the platform offers, and we'll introduce the Python environment for image analysis and also the rich image analysis APIs. We're going to discuss the workflow for processing a collection of images, and we'll deep dive into each step and demonstrate with two use cases. One is the annual maximum and event trend analysis using time series Landsat image, and the other is we want to look at and analyze the cover changes using linear spectral and mixing. So here is a comprehensive overview of the ArcGIS platform for imagery. It contains managing and disseminating imagery and providing rich image content from ArcGIS Online, and has many visualization techniques for satellite imagery, for oriented imagery, oblique imagery, motion video, and so on, and also the capability to visualize spectral profile and temporal profile and things like that. The ArcGIS auto mapping capability allows you to process aerial images like drone images and also satellite images and generate the digital elevation model and generate auto mosaics. And last but not least, which is the rich analysis capability that allows you to extract useful information from imagery. So we want to take a little bit detailed look at the data management and analysis capability, which will provide good context for this presentation. For data management, we use mosaic dataset to manage imagery. It supports many types of images, many types of satellite data, for example, Landsat, MODIS, and Sentinel data, 1, 2, 3, 5, and you name it. And this mosaic dataset reference the image data. It doesn't copy or doesn't store pixels, but manage the metadata of the image so that you can support quick query. And then you can also define processing template to the mosaic dataset and to be used in the on-the-fly processing. Mosaic dataset data model is scalable. You can manage massive, large collection of images. And another data model is multidimensional raster, which is used to manage multiple rasters or store multiple rasters in one file. And this multidimensional raster has well-structured metadata such as variables, dimensions, dimension values, so that you can do quick query of the data. And multidimensional raster support many multidimensional raster analysis. These two data models can all be served as image services. So through ArcGIS image server. Image server perform on-the-fly processing, on-the-fly mosaicing, and it can also be you can also persist the analysis result. For analysis, ArcGIS support many image classification methods, such as random forest, the SVM method, and of course the maximum likelihood classification method. It also has the capability of deep learning, machine learning, and trend regression, and many multidimensional raster analysis capabilities. So these capabilities are exposed as geoprocessing tools, services, and also comes with pro user experience. For example, managing training samples or deep learning labeling and so on, so which are used to complete the workflow of image classification or deep learning. ArcGIS also has many raster functions for processing image and raster data. These functions perform on-the-fly processing and also can persist the analysis result. And you can leverage the Raster analytics server to scale up and distribute the analysis for large data sets. And ArcGIS also comes with a Python environment for Python users. All the image capabilities we went through in the previous slides are also available for Python. So the platform comes with two packages. One is ArcPy, which is a desktop solution. When in this package, there is a ArcGIS.RA module, which is the image analysis module. So in this package, it contains many classes, functions, and operators that are designed specifically for image analysis. So it is very user-friendly and in a style, in a so-called very Pythonic style, and easy for Python users. ArcGIS API for Python is an enterprise solution where you work with services and perform analysis on server. The API and the capability we will talk about in this presentation are only released in ArcGIS Pro 2.5. So we're going to, in this presentation, demo and code snippets, we're going to use ArcGIS Pro 2.5, ArcPy, and ArcGIS Notebook. Similar capability on ArcGIS API for Python will be available in the next enterprise release, which is ArcGIS 10.8.1. So before we get into the advanced workflow, I'd like to start with this simple example to warm up. I think it's useful for people who haven't used ArcPy before. This is processing single image. For example, create an NDVI out of a Landsat scene. So to work with single image, we use Raster class. Raster class contains bands, and you can create a raster object directly from a file on disk using arcpy.ra, using arcpy.raster method. You can use arcpy.ia render function to display the raster, display as RGB or false color. And then you can apply a NDVI function and then display the NDVI result raster using a color ramp. So very easy, straightforward, a few lines code, and you can get the analysis NDVI raster. In many cases, you want to work with a collection of images. The Landsat images has about 40 years of data with 16 days interval and many bands, which allows you to extract information. And with this amount of data, you can answer. It actually provide a lot of information than a single image could have. For example, answer questions like what is the water occurrence in the past 10 or 20 years? Did deforestation happen in this area? Or what are the land cover changes and what's the pattern and things like that? So you want to work with a collection of images. So here is the workflow of ArcGIS to work with a collection of images. And you create a ResCollection from your images, and then you filter the items, the images that fit to your application. And then you use map to map a processing algorithm to each item in the collection. And then you reduce by aggregating the items or by summarize the items into an analysis result. So to further explain the workflow, we will take the first use case, and we deep dive into each step. So in this example, we want to look at the vegetation trend in the time series data, and the input is 173 Landsat scene, and we want to process and generate a trend raster out of these collections. So the first step is create a ResCollection. A ResCollection is an object, is a class, defines a collection of rasters for processing. So it is defined by a list of raster and its attribute, which is the dictionary of keys and value pairs. And we also call a raster plus attribute as an item. So a ResCollection has many items, and each item is a row in the list, as you can see on the right side of the screenshot. And each row has a variable name, the file name, and the time, and so on. So you can actually define many attributes from the metadata of the data. The images defined as attribute. There are many ways to create this ResCollection. And the first, very straightforward way is to just create from the file. You define a list of file names and the associated attributes of the file and create a ResCollection. And this is useful if you don't want to spend time to learn the data model, mosaic dataset, or image service. You can create on your own directly from the file. And but sometimes your organization or your team might already have a mosaic dataset created, so then you can create directly from mosaic dataset. And sometimes actually, if you have a folder whole of images, it might be easier for you to create a mosaic data first, which will automatically extract the information, the metadata, into the mosaic dataset. And then you create directly from the mosaic dataset, create this raster collection from mosaic dataset. And of course, you can create from image service or multidimensional raster. So for more information about the data model, mosaic dataset, and image service is multidimensional raster, and here I have the help links you can check out later. So you have the initial ResCollection, and next you might want to filter the items that fit to your project. For example, you want to select by time range, select by area of interest. So here we provide many methods, many ways for you to filter the image. You can even filter by geometry. For example, you define a line representing a river. You can find the image that across the river, or you can define a polygon that you find it, or the image or the scenes within the polygon or across the polygon, or things like that. So there are many ways you can filter the items based on your project's requirement. So after filter, I got the items, the ResCollection that has the items that I need to used to analysis. So this step we call the map. This is the core step in the whole processing, is where you apply your analysis algorithm. And it has a similar style like a Python map function. And here in ArcGIS, this map is we apply an image processing algorithm to the item within this Raster collection. So all you need to do is to define a function that works on the item. So here is a little code snippet. It takes the item as the parameter, and you get the raster from the item, and you define your processing by calling existing function, or you write a custom function. And then you return this function as an item, and then you call ResCollection.map, map this function to process each item in the collection. So this code example is the NDVI function that defined. So we create an NDVI ResCollection. So as we said, this step map is a very core step in the whole process. And ArcGIS provides many existing functions, built-in functions for you to work with. For example, the band index functions. We use NDVI, but there are many more, like NDWI, water index, and there are also index for burn area, for ice, for fire, and things like that. So, and you can also create your own function based on using the band arithmetic function. Just compute between using the band as input. And there are also many heavy-duty functions like classification, random forest, support vector machine, maximum likelihood, and also the linear spectral mixing, which will be used in the second demo. There are many other functions like pixel stretching, parent sharpening, and also analysis function. And this apply function is a generic function which allows you to use, for example, you in ArcGIS Pro you create function template by chaining many Raster functions, or you have written custom Python Raster function. So you can use this ArcPy function to apply these processing into your ArcPy environment. Of course, you can develop your own function just using NumPy array and writing how you process pixels. And after you get the analysis for each item, next is to reduce by aggregating the item or summarizing the item into a meaningful analysis result. And Raster Collection provide a few methods, which is like min, max, summarize, sum, which, for example, min will calculate the minimum pixel values across all the time, across all the items within the collection. And in this code example, we calculate the actual maximum values across maximum NDVI value across all the items. And then we get one single item. And so this is, actually in many cases, the reduce is not just as simple as summarize, as max and min. It can be more complicated. For example, if I want to look at the trend using the items within that collection, so I can actually leverage the multidimensional Roster analysis capabilities. To do that, you use this two multidimensional raster to convert the ResCollection to a multidimensional raster, and then you use the functions that build for the multidimensional raster. For example, in this example that Casey is going to show, which include the aggregate and trend function. So then we process and aggregate and generate a trend raster as the final analysis result. Okay, so we went through step by step over the whole workflow, processing image collection and apply analysis algorithm and generate a result. Now we're going to look at two demos. Okay, now I'm going to switch to Kaishi.
So, thank you, Hong. So let's take a look at the first use case. So this is to show the annual max NDVI from the time series to Landsat image. So Hong has showed it in each step using the slides. So now we take a whole picture. Okay, so first we need to import the package, especially the ArcGIS, and we check out the image analysis extension. So this is our workflow. So in the beginning, we have a full time series Landsat image, and then we do a filter, choose some out, and we map a NDVI function to each thing. We convert the connection to a multidimensional raster. And because use the multi-dimensional raster, we can easily do aggregate like by yearly, by monthly, and so on. And we have other like intervals you can use. Once we have the annual max NDVI, we can apply the trend function, and then we can get the trend raster. We can see like which area has NDVI increasing in the time series period, and which area has decreasing. Okay, let's go through it. So first, we create the Raster Connection from a date folder. So I got this date folder from my colleague. So he downloaded the Landsat things and put it in the shared folder. And in this folder, we have a lot of Landsat things. So here we use a Python way, like just to iterate through each subfolder and get the Landsat name and also the raster. At the end, we get a list of raster, a list of names, and a list of time value, the time. So here, we use arcgis.ia.raster connection. We give the list of raster here, and then a dict, which shows the attribute for each item. At the end, we get a raster connection object. We can check how many items in this raster connection, so we get like 173. Next, we do a filter. So here we are interested in the things not between 2000 and 2009. So we use the raster connection.field by calendar range, give the calendar field year. So, and the start is 2000, and then the end is 2009. So we get a new raster connection, which only has the item not in between 2000 and 2009. And we can check the count again. So now we only have 93 items in this connection. We can display the raster connection and use in a graded format. So each row here is one item, and then we can see the attribute for value for each item, like the variable, the name, the time, and etc. So you see in total we have 93 rows because we have 93 items. In addition, we can also visualize the raster in each item. So here, I choose the first item and then get the raster from the first item. Use the arcgis.ia.render, give a RGB rendering rule, and then we can see how it looks like. So this is the thing in the first item, and you can see there some cloudy area. So the next step we use is to do the pre-processing to mask out the cloud shadow and S these things. So to do it, we define a raster function, a Python function called the clean, and the input is item. From the item, we can get the raster. So for each raster, we use the for each item, we also got the quality raster, and we know like in the quality band, like this pixel are our like cloud, water, snow, and ice. So we want to like remove it out. So we create a mask raster that in which 1 means the value we want to keep, and 0 means these pixels are cloud related. So we want to mask it out. And then once we have the mask raster, we use the arcgis.ia.apply, apply this mask to each band, to the blue band, green band, red band, and etc. And then we can get a multi-band raster in which each band has cloud mask out. And for the return, we return a dictionary in which there is a special key called raster. Here we give the mask out multi-band raster and some other attributes. So once we have the Python function, we can use Raster Connection.map, give the function name, and then you can get a new raster collection in which each item has the cloud mask out. Then let's see how it looks like. So still the first item, here we check how the raster looks like now. So you see the white area, actually this pixel has been masked out. And next, we want to calculate the NDVI. So we define a Python function called calc NDVI. We use the arcgis.ia.ndvi, and the first input is the raster from the item, and then we give the band for the linear infrared and red. Now we have an NDVI raster. We return it as the value of the for the key raster, and then some other attributes. So the same, we use the Raster Connection.map. So now we have a raster connection in which each item has the NDVI raster. So let's see how the NDVI looks like. So yeah, so the raster in the same item as before, but now it shows you the NDVI value. Okay, now we have a collection contains the NDVI for each thing. And what we want to do next is we want to calculate the max NDVI in each year. So we can use Raster Connection .max. So it's a reduced method to do it. But this means like to do for each year, we have to write like a Python loop. So for each year, we choose all the items in a specific year, and we do a Raster Collection.max. And then we can get the max NDVI in that year, and we do a loop. So we got the max NDVI for each year. So we can do it use Raster Connection, but there is a more convenient way to use multidimensional raster. So here you can convert your Raster Connection to multidimensional raster. Use the Raster Connection.toMultidimensional raster. You give the attribute name that you will use it as a variable field, and you give the attribute field that you will use it as a dimension field. So now we get a multi-dimensional raster. Each slice is an NDVI, and we can use arcgis.ia.aggregate. Then we want to aggregate a long time, and the function will be max. And here, the key point is the aggregation definition. We set the interval as yearly. So in this way, we will calculate the max NDVI in each year. We will also have other options like monthly, daily, and recurrent monthly. You can check out later. So now we have a multi-dimensional raster in which each slice is the max NDVI in each year. So next, we apply a trend analysis function to the multi-dimensional raster. The trend analysis function, we give the argument, like the trend analysis will be down along the time dimension, and the regression type is 0, which means it's linear. So after that, we get a trend raster. The trend raster has 3 bands. The first band is slope, the second band is intercept, the third one is root mean squared error. So for visualization, here I choose the first band, so which is, I get a slope raster. And then I do a little tricky thing, because in the slope, if it's positive, the pixel value is positive, it means it's increasing, and it's negative, it means it's decreasing. So here, I first use arcpi.ia.remap. So I change all the positive values in slope to 1, all the negative pixel value to 0. So now I have a Boolean map. And then let's say I use arcpi.ia.render and give different color for the Boolean value. So we can see how it looks like. So now the dark green area, which shows that it has NDVI increasing through the time period. And then the area that in gray color means it has NDVI decreasing. Okay, and then next, you can save your output. So I want to save the trend raster, so you can easily use raster.save and give a path, and it will save as a CRF on your local folder. So next, we will show the second use case, which is to analyze the land cover change using linear spectral unmixing. So linear spectral unmixing is a sub-pixel classification. So normally, we do classification, we assign a category to each pixel. But in this method, for each pixel, we calculate the percentage of each category in 1 pixel. So here we use a Landsat image, time series Landsat image, apply a linear unmixing function, and what we get as the output is a time series unmixing result and also the statistic output. So let's go back to the demo. So in the beginning, still you need to import the package, the ArcGIS, and check out the image analyst. And here for classification, we are looking at 3 categories. So the first one is non-photosynthetic vegetation. So it's short for NPV. So which actually is some leaves and dead vegetation. And the second one is photosynthetic vegetation. So it's green vegetation. And the last category is bare soil. So normally, we can classify 1 pixel into the fraction of the 3 categories. So for this area, is actually a mixed of these 3 categories. So we want to know what's the fraction of each category in this area. So this is what unmixing trying to do. Okay, so let's take it. So I got a mosaic dataset from my organization, in which actually covers California. So in this Raster Connection, I have 1,087 items. And next, I do a field. In this case, I filter first by geometry. So I define the area of interest. And then I use Raster Connection .filter by geometry. And in this case, only the item that has intersection with my study area will be returned in the output. And the next, I do a further filter by time to only look at 1990 to 1999. So after the geometry field and the time field, now I only get 126 items in my new connection. So the same, you can visualize it. So 1 row is 1 item here, and you can visualize the raster in the item. So you can see in this area, it's actually very cloudy. So next, we do the same thing as shown in the first use case. We remove the cloud, the shadow. So I will go quickly for this part. And then for the visualization, you see, yeah, the white area is actually the pixel that has been masked out. Yeah. Now the analysis comes. So the linear unmixing, here we define a Python function to do it. So the input is the item. First, we get the raster from the item, and from the raster, we can get each band. So here, we have 6 bands, and based on the 6 original bands, we calculate the log, we calculate the product. So we do a simple analysis. So at the end, from 6 bands, we expand it to 63 bands in total. So this is the new bands we have. And next, we create a JSON file that contains the end member for classification. So the end member shows like what the spectral value looks like for a pure category. So in our case, it's the spectral value of the non-photosynthetic vegetation, the spectral value for the photosynthetic vegetation, and the spectral value for the bare soil. And based on that, we use the arcpi.ia.apply. So this is the 63 band raster that we generated above, and then we give a spectral unmixing function, and then the end member we put it here. So after apply the spectral unmixing function, we get the unmixing classification result, and then we return it as a dict. So the spectral key is the raster, which its value is the unmixing raster, and some other attributes. So once we have the function, we can use the map. So Raster Connection.map gives the function name. And now we get a new Raster connection in which each item is the unmixing result. So here for visualization, we choose the same item as before and see how the unmixing result looks like. So you see on the left side it is mostly is green color, is because this area has a larger proportion for the vegetation, and because this area actually is forest. And on the right side, it looks like blue, it's because it has a larger proportion of bare soil, which is logical because this area is urban, it's covered by city. Yeah. Okay. And next, I want to show you how we can do reduce region. So now, I have a county polygon boundary, shows the county boundary, the shapefile. And I want to know the average amount of each category in my county along the time. So first, we use the for loop. So we go through each item in my unmixing Raster connection. We choose the item, and then we use arcpi.ia.clip, and we apply the county boundary to the raster. And at the end, we get a new raster which clipped out by the county boundary. And then we can read the pixel from it, and then we can calculate the mean for each category at each time. And then we use the Python way to plot it. So yeah, so this is how it looks like. So the green color here shows you the percentage, the average percentage of the photosynthetic vegetation category in my county, and the red color is for non-photosynthetic vegetation, and the blue one is for bare soil. So you can see there are some seasonal change along time. But yeah, you can also notice that there is a sudden drop at 1992 September. So what caused it decreased rapidly? So we checked online and we found that actually, I need to run it again. Actually, there is a fire, a big fire occurred in this area in 1992 September. So the fire actually caused the drop of the vegetation amount. But you can also see there is a recovery after the fire. So the fraction of the vegetation start to increase for the rest of the years. Yeah. For the linear and mixing method, we actually set this paper, so we use the method from this paper. Yeah. Okay, that's it.
Okay, thank you. Switch. Yeah, thank you, Kashi, for this two interesting demo. So now, until now, we have gone through the workflow of processing and analyzing time series image, and we walk you through with these two amazing demos. And I have a couple things to mention. There's another way of processing a collection of images, which is you mosaic those images. So Raster Collection has a method mosaic, which allows you to mosaic the items in the collection. For example, you want to produce a mosaic like a cloudless mosaic. Kashi used a few the cloud remove method in her demo, in the two demos, right? So you can make a mosaic. So here the code snippet is that you can, for example, you can sort the images by the time, acquisition time, and you can, specify the band that you want to mosaic, and then you just call the mosaic method. By passing argument, you can choose like first or last, and this basically can produce a mosaic that has most recent pixels from the image. And then you save the result. Some things I'd like to mention on the process settings. You see during the whole process, many steps actually you don't have to save data. It's all processing on the fly. But there are certain steps you do. For example, you create a large mosaic, or you do a reduce from a long list of items, large image collections, and you can save out. You can save to a CRF file, which is a format, cloud raster format, that this format can store one image or multiple images as a multidimensional raster, and it is tile-based and support parallel processing. And of course, you can save to TIFF as well. And you might want to set the compression method to reduce the size of the output. And LURC is a compression that is developed by Esri, which is a very efficient compression algorithm. You can actually control the accuracy while you compress the data. For example, scientific data, sometimes you will produce floating point data, like NDVI or average of the pixel values. In this case, you can specify you want to maintain 1 or 2 or 3 decimal place accuracy. So you can do that. Of course, we support many other compression algorithms. You can define your processing, parallel processing factors, then all the process will be parallelized. And you can use a percentage, like 90% of your processors within your computer can be used to process the data. Or you can specify the number of processing for your analysis calculation. And here are some hyperlinks. And first one is the Raster collection class, so you can check out. And another is the whole list of the image analysis function help. So with that, you can create your own applications. And the same capabilities and APIs we demonstrated in this presentation will be available for ArcGIS for Python, and this will be available in ArcGIS 10.8.1. And last, I like to end this presentation with this very beautiful nightlight trend map. This is the input is USGS nightlight data from 1992 to 1913, which is 20 years, and then we run trend function and create a trend raster using ArcPy, and then we convert this trend raster into an RGB, which we map the positive trend, positive slope into red, map the negative slope into blue. So then red pixels means increasing, blue pixels means decreasing. And we know from many studies have shown that the nightlight data has directly, the population growth or urban expansion has a direct relationship with the nightlight data. So with this, we can see that the urbanization, urban expansion happened globally, while it is increased greatly in the eastern countries, while slowly, relatively, in the western countries. So this is all the presentation we have for today, and thank you for watching.